So now I'm going to pick up the pace a little bit, just talking about our standard electrode potentials and where these actually came from. The scientific community has universally sort of accepted that this standard hydrogen electrode, which I'm going to show you here in a minute, um, we assign that as 0 volts. So every other cell potential has been measured in conjunction with that standard hydrogen electrode, so their potentials have been measured. So you can see here in the diagram, you have a zinc anode with this standard hydrogen electrode. And just I'm pulling up here the line notation. So again, this is your anode and this is your cathode. And this is the representation of the standard hydrogen electrode. You have hydrogen ions at 1 molar using the form of, in this case, hydrochloric acid or some sort of acid. You have hydrogen gas that's being bubbled through into this cell, and then you have this platinum metal, and the platinum is an unreactive metal that allows electrons to be transferred without losing any of that electronic charge. Okay, so here's what's going on at your anode. Here's what's going on at your cathode. We put those together and we get our overall reaction. As you can see from the digital voltmeter up here, that reads 0.76 volts. So the standard reduction potential, or the standard cell potential, is associated with that reduction when all solutes are at 1 molar, all gases are at 1 atmosphere, and you have this standard hydrogen electrode, which, like I mentioned, we assign as 0, and then look at all the other potentials with respect to that. So here's your reduction reaction. Okay, that again equals 0 volts. And this page, this is a real important page. You'll be sort of referencing it a lot. It is the table of reduction potentials for many of the common half reactions. As you can see, they're all written as reductions. And hopefully, as you know, whenever we put these cells together, we're always going to have a reduction and an oxidation. So one is always going to have to change from how it's written here to an oxidation reaction. Okay, and we just flip the reaction. And as you're familiar with in terms of, say, Hess's law and delta H values, when you switch the reaction, you change the sign on those, and you change the sign as well on the cell potential. You can see here is the standard hydrogen electrode labeled at 0. All of these in terms of with respect to this are reductions, and really all of these, when you put it together, are actually oxidations. These are more apt to be reduced, these up here. These are more apt to be oxidized down here. So these are reducing agents, and these up here are oxidizing agents, and they're all in a row. Sometimes you see this as one big sheet. This just happens to be 2 columns. Okay, so the cell potential is for the reaction as you see written there. The more positive the standard cell potential, the more tendency it is to be reduced. Okay, so it's a strong oxidizing agent if you see a positive value. They are reversible, and the sign of the cell potential changes when the reaction's reversed. And when you put a full cell together, you're always going to be reversing one, because with a reduction, you have to have an oxidation. And then finally, this is something that's different. So this is not the same as what we would do with Hess's law. When you change the stoichiometric coefficients, which is important because you do have to balance the reactions, you don't change the value of the cell potential. So let me just say that one more time. If you multiply one of these electrochemical reactions by 2, you do not change the value of the cell potential by a factor of 2. The only thing that you need to do is if you flip the reaction, you change the sign.